Chapter 4 Electrical Systems Knowing What's What. A simplified approach for those with little or no understanding of electricity. Welcome to Volts for Dolts, the Machado quick course for those afraid of electricity.
Dude, check it out. Attention, this class is going to be easy. What? Easy? Yeah, because we're going to learn what electricity does, rather than split atoms over what it is.
Let's be practical. You want and need to know how to detect and direct electrons in your aeroplane and put them to work for you. You also need to know when the electrical system is threatening to roll over and play dead, and what can be done about it. Read on, fear not, think volt, not bolt. Electricity and water. Albert Einstein once said, "Make everything as simple as possible, but not simpler." For instance, Einstein's concept of time distortion is often discussed from a mathematical perspective. For most of us, this is like listening to a lecture delivered in Martian, actually Southern Martian. On the other hand, suppose someone said that the length of 1 minute depends on which side of the bathroom door you're on. Now we're communicating. Unfortunately, the philosophy of simplicity has not been applied to understanding the aeroplane's electrical system until now. We're going to approach this like a plumber, by thinking about electricity as though it were water. This may be the only chance you will ever have to mix electricity and water safely, so pay attention. A water model of electricity uses basic plumbing language to explain how electrons flow in a circuit. The only problem with the model is that you can't use it to build a computer. The model's language isn't precise enough to describe the intricate electrical nuances necessary to accurately convey the point. Besides, what would you do if water suddenly shot out of your hard drive? You can, however, use the water model to describe, accurately enough to suit any normal private pilot, how an airplane's electrical system works. I caution you not to take this model literally, and if you actually are knowledgeable about things electrical, I also urge you not to take offense. The model is only used to help clarify certain cause and effect relationships. One more disclaimer. This model uses conventional current flow, where things go from positive to negative. In reality, electrons flow from the negative to the positive side of the battery. The reason for the difference lies in physics theory. But that's not what this book is about. I use conventional flow because it makes much more sense to mere mortals when things flow from high to low, plus to minus, big to little, etc. Electricity involves many terms that can be directly related to water or plumbing. Voltage is comparable to and can be thought of as the pressure that pushes water through the pipes. Current is the amount of water actually flowing through the pipes at any given time. The greater the water pressure, in other words voltage, in a line, the greater the amount of water, or electric current, that can flow. For electrical equipment to work, something must provide voltage or electrical pressure. In most airplanes, this device is called an alternator. Using the water analogy, the alternator can be thought of as the pump which provides water pressure to the primary bus and the avionics bus. In the electrical world, a bus is a pathway for electricity, not a yellow conveyance for kids. A bus is essentially a drinking trough for hungry electrical equipment. Normally, it's a piece of conductive metal that thirsty electrical equipment taps into when drawing the electric current it needs to operate. From now on, I'll speak of electricity in terms of the water analogy as often as possible and, when possible, discuss how it relates to electrical theory. The water pump. Where might the water pump get the water it needs to pressurize the primary bus? Imagine a tray of water resting on the ground. The water pump draws water up from the tray and pumps it into the primary bus. From here, the water flows to the electrical equipment, where it does useful work. Then it flows back to the tray resting on the ground. This completes the circuit, allowing the water to return to its original source. Electricity follows a similar circuit. A spinning alternator causes electric current to flow into the primary bus and through the electrical equipment, where it lights up lights, spins up motors, spins round gyros, and otherwise makes things go bang, wang, and clang in the night and day. After leaving the electrical equipment, electric current flows back to its original source in a manner similar to the tray in our water analogy. The tray is called the electrical ground. For electrical circuits to work, electric current must have a way of returning to its original source. Electric current flows from one side of the battery through the light bulb, thereby doing useful work, then back to the other side of the battery. If the return wire is broken, there is no way for the current to return to its source, and the light doesn't shine. Even though the wires are not connected, the light shines because the bulb and one side of the battery are connected to an electrical conductor, which allows electricity to flow between them. This conductor is the electrical ground, which is represented by small slashed triangles. The electrical ground. The electrical ground is not the ground upon which you stand. It's usually the aeroplane's metal frame, which is a great conductor of electricity. The frame acts as one large wire, returning current to the alternator or any other piece of electrical equipment that's connected to the electrical ground. It is similar to the water tray in our water analogy, which allows water to return to the pump. Since the alternator is connected to this electrical ground, the circuit is completed as electrical current returns to its original source, the alternator. Load meter. A load meter is located between the pump and the primary bus of our plumbing system. In other words, it shows how much water is demanded from the pump by the aeroplane's water, in other words, electrical, equipment. If the load meter reads 0, a full deflection to the left, either the pump isn't providing any pressure to the primary bus, or the electrical, in other words, water, equipment simply isn't demanding any water. Load meter readings above 0 represent the pump's water output. This output should equal the total draw by equipment connected to both buses. The load meter provides similar information about alternator output in an electrical system. A 0 reading means the alternator isn't providing electricity to the primary bus, or there is no electrical current drawn by the aeroplane's electrical equipment. This can happen because the alternator is disconnected from the bus, the alternator has failed, or all the aeroplane's electrical equipment is turned off. Load meters are also known as ammeters, and their readings are calibrated in amperes, abbreviated as amps. Amps are a measure of current flow, equivalent to gallons per hour of water. If the aeroplane's electrical equipment demands 30 amps of current from the alternator, the load meter should indicate a 30 amp needle deflection. The alternator circuit breaker is also located between the alternator and the primary bus. Circuit breakers protect electrical equipment and wires from receiving more current than they can safely handle. By now, you should have a fair understanding of how the electrical system works when the alternator is turning. But since the alternator is driven by the engine, what source provides current for the aeroplane's equipment when the engine isn't running? The answer is simple. It's the thing missing from most children's Christmas presents, a battery. The battery. Using the water analogy, the battery can be thought of as a box containing a thin, square piston with a powerful spring on one side. The battery's square piston is capable of sliding toward or away from the spring depending on whether water flows into or out of the battery. Water flowing into the battery is said to charge it. Water flowing out of the battery drains or discharges it. Since the primary bus is already pressurized by the spinning pump, water should easily flow into the battery. As it does, it pushes the sliding square piston to the left against the spring. The battery has now stored water pressure and can be thought of as being fully charged. In the event the water pump stops working, the battery provides water under pressure, in other words electrical current, to the primary bus.
Have you ever used a pressure-type thermos to store your coffee? It's the kind where you put in the coffee, pump the handle on top, open the spigot, and out squirts coffee. The thermos stores coffee under pressure so that caffeine-hungry pilots can quickly slake their thirst. On late-night flights, pilots often lock their lips onto the spigot, push the handle, and absorb just enough caffeine to vibrate through solid matter.
In an electrical system, the battery chemically stores the electrical charge provided by the alternator. The process is different, but the principle is the same as that of the coffee thermos. Most airplanes have either a 12 or 24-volt battery. Think of a larger battery as one with a bigger spring that puts the water under greater pressure. It's the battery which allows you to operate the airplane's electrical equipment when the engine isn't running or when the alternator fails in flight. Battery potential. You should know how much electricity your battery stores for one good reason: in-flight alternator failure. How much power the battery stores is indicated by its amp-hour rating. A 35 amp-hour battery should, in theory, provide 35 amps of continuous current to the electrical system for 1 hour. In other words, if the electrical equipment draws a total of 35 amps, the battery should run that equipment for 1 hour before it's depleted. I say theoretically, because this rating assumes many things: a new battery, a new electrical system, ideal conditions, and perfect harmony with the universe. In reality, many battery engineers, people with 2 terminals protruding from their necks, say that you should only count on half of the rating. In other words, 35 amps for 30 minutes or 17.5 amps for 1 hour. You know those federal ratings of how many miles per gallon some shiny new car will give you? Keep in mind that there's always a little disclaimer, the one that says, "Your mileage may vary." Very right, and it's not likely to vary on the high side. While aeroplane batteries are rated at 12 or 24 volts, aeroplane electrical systems, their alternators, are rated for 14 or 28 volts. Why does the alternator have a higher voltage rating than the battery it charges? It's a lot easier and quicker to charge a battery to its full potential when the alternator pressure is stronger than the battery pressure. If we want the pump in our water system to store water in the battery, the pump must provide a little more pressure than the spring to push the piston back. The alternator's extra 2 or 4 volts is all it takes to keep the battery charged, in other words, to push against its chemical potential. The charge-discharge ammeter. Between the positive terminal of the battery and the primary bus is another version of an ammeter found on some airplanes. Ammeters of this variety are often called charge-discharge ammeters. As the name implies, the charge-discharge ammeter tells you if electrical current is flowing into or out of the battery. This directly informs you about your electrical system's state of health. Whether you have a load meter or a charge-discharge ammeter depends on the specific make and model of your aeroplane. Most aeroplanes have one or the other, but seldom both. Current flow from the primary bus into the battery is indicated by a positive needle deflection. Think of water, or electrical current, pushing the needle toward the plus or negative side of the ammeter as it enters or leaves the battery. A positive deflection usually implies that the battery is being charged, water is moving into the battery. A negative needle deflection indicates that the battery is supplying the primary bus with electrical current. In other words, water is moving out of the battery. Normally, the needle should be resting near the zero or center mark. This implies that the battery is neither being charged nor discharged. A good sign. Continuous needle deflections too far from center, however, are cause for concern. There are circumstances where the needle will indicate a large deflection from the center position for short periods. Starter motors demand large amounts of electrical current for their operation. After startup, the battery is sure to be slightly drained. Expect to see a positive needle deflection of 5, maybe 6 or 7 needle widths on the ammeter right after engine start. This means that the alternator is replenishing battery energy consumed by the current-hungry starter. Expect a similar ammeter indication if the radios were used extensively prior to engine start. But beware, too much charge is not a good thing for batteries or credit cards. Most airplane operation manuals suggest that after approximately 30 minutes of cruising flight, the ammeter needle should return to within a 2-needle width deflection from the center of the positive or charging side. A larger positive needle deflection suggests problems with the battery or the alternator. A runaway, unregulated alternator can provide too much current and overcharge the battery. This is usually indicated by a large positive needle deflection, more than 1 or 2 needle widths. The excess voltage can boil off battery fluid, electrolyte, damaging the battery and possibly causing a battery fire. A needle deflection on the negative side means current is flowing out of the battery onto the primary bus. It also means the alternator isn't providing the necessary voltage to keep the battery charged. This situation is similar to a flight instructor's bank account, where more is going out than is coming in. Chances are the alternator has failed, has been automatically disconnected from the system, or is being improperly regulated. Any way you look at it, you have a problem. The battery will eventually lose its charge. This situation is best handled by conserving battery energy, turning off everything you don't need, and if necessary, landing at the nearest airport. Remember, you may need battery power to lower the landing gear or flaps, or power the landing lights if flying at night. This is why good pilots carry flashlights, and bad pilots use flashlights to carry their dead batteries. A nearly centered charge-discharge ammeter needle usually means an electrical system knows what's what and is taking care of business.
In the early 1980s, Rod had the pleasure of checking out an airline captain in a Cessna 152. He had a wonderful time learning the systems and flying the aircraft. He did quite well except for one thing. On every final approach, he would call the tower and say, John Wayne Tower, this is United Heavy. We're on a long final approach for 19 left. The controller thought this was really funny. The pilots of the little planes on short final for runway 19 left didn't. The thought of an enormous metallic Pac-Man gaining on them was downright scary. Attempting to understand the electrical system is somewhat like being the guy on short final for 19 left. It's scary at first, but when you get a good, clear look at the threat, it's not so bad after all.
Hopefully, you haven't been scared by the electrical system so far. Let's return to our discussion on load meters and discuss it in relation to the aeroplane's battery. Load meters. There are benefits and disadvantages to almost everything you do. For instance, whenever I travel to a location for a speech, I always get the most economical airfare for the client. However, economy is not without its disadvantages. On my last flight to Nome, Alaska, I had 4 plane changes. Unfortunately, 2 were in flight. Load meters in lieu of charge-discharge meters have their benefits and disadvantages. Essentially, they both provide pilots with the same type of information, but in a slightly different format. Load meters provide important indications about the health of the aeroplane's electrical system. Unlike charge-discharge ammeters, they are calibrated to reflect the actual ampere load placed on the alternator. Remember, most airplanes will have either one variety of ammeter or the other. Load meters with a 0 or full left deflection indicate the alternator isn't providing current to the primary bus. Any electrical equipment that's in use must be receiving its electrical energy from the battery. A full left deflection of a load meter needle is similar to a charge-discharge ammeter reading pointing to the negative side of its scale. Load meter needle deflections to the right of the 0 index represent the electrical current drain on the alternator. Another way of saying this is that a right needle deflection represents the alternator's output. If you add all the electrical current used by the active electrical equipment, this sum should be equal to the amount of the needle deflection. After all, the alternator should be producing what the system demands. Otherwise, battery energy is being drained. Electrical drain. If you're piloting an airplane equipped with a load meter, you need to know how much electrical current each piece of electrical equipment consumes. Think of each piece of electrical equipment as having a minimum thirst level. Some equipment needs more water or current to operate than others. Amperes are a measure of the amount of electrical current consumed by each of the aeroplane's electrical items. Understanding how thirsty each electrical item is the key to understanding if your alternator is working properly. Radios typically consume 1/2 amp of current while receiving and about 5 amps while transmitting. Nav radios and gyros require about 1 amp, transponders about 2 amps, autopilots about 10 amps. Full de-ice equipment, this is special equipment for advanced airplanes, might gulp as much as 70 amps for continued operation. With 2 receiving radios, 2 navigation radios, 1 electric gyro, a transponder, and an autopilot in use, a 16 amp deflection should be shown on the load meter. A needle deflection less than 16 amps implies that the alternator isn't providing enough current to run the equipment. Where will the extra electrical energy come from? Need a hint? There's only one place: the battery. Needle deflections less than the summed amperage of active and properly working electrical equipment imply that the battery will eventually be drained. That's why it's absolutely necessary that you know how much current each piece of electrical equipment draws. Suppose the load meter's needle deflection is greater than the needs of the electrical equipment. This is similar to a charge-discharge ammeter indicating a large positive needle deflection. In either case, such indications suggest that the alternator isn't working properly, or that there is a leak in the electrical plumbing, otherwise known as a short. Soon, we'll discuss how the alternator is regulated and why it may develop problems. Load meter indications in excess of the system's electrical demands are the system's cry for help. Ignored, this cry can lead to unhappy results, such as evaporating battery fluid or battery and electrical fires. This is referred to as a battery losing its cool. You, in turn, will lose your juice. Remember, the alternator needs to replenish the battery energy drained by extended use of the starter or radio, so expect to see a slightly higher load meter reading immediately after engine start. I always make it a point to look at the ammeter right after engine start for two reasons. First, I get a sense of battery health by observing how fast the ammeter needle returns to its normal position after starter use. A failing battery will show up as an ammeter needle taking progressively longer to return to a normal position. Establishing a trend of needle response over a long period of time makes needle movement even more meaningful. Second, starter motors have been known to stick and not disengage. Actually, it's the starter's contactor that sticks, but the results are the same. If this happens, the starter remains engaged, guzzling enormous amounts of battery current. You might not be able to hear the engaged starter once the engine is running, but you will see a very, very large negative needle deflection on the charge-discharge ammeter right after engine start. On aeroplanes with load meters, a stuck starter contactor might be identified by an abnormally large reading, indicating an enormous drain on the alternator. Shut the engine down immediately if you see this type of unusual needle deflection right after starting the engine. Don't be too concerned with ammeter needles that wiggle slightly. Ammeters have needle dampening mechanisms in them to steady wiggling needles. Sometimes these mechanisms just wear out. As a student, I thought it was my careless application of rudder that caused needle wiggling. I mentioned this to my instructor. He said that this wasn't possible since I never seemed to use the rudder. If we see an unusual ammeter or load meter indication in the air, should we land as soon as possible? It depends. There are several things we can do about airborne electrical problems, but solving them requires an understanding of how alternator voltage is regulated. The voltage regulator. Airplanes with complete electrical systems have voltage regulators or alternator control units. They're essentially the same thing. As the name implies, these devices regulate the alternator's output. If the engine is turning the water pump, alternator, it's logical to assume that higher RPMs produce greater water pressure. In an electrical system, this results in alternators producing variable voltage. This would wreak havoc with electrical components that demand consistent voltage for accurate operation. Fortunately, voltage regulators, the brains of the electrical system, help alternators maintain a constant voltage output under variable RPM conditions. Voltage regulators consist of transistors, diodes, capacitors, and possibly relays and contact points. Describing the working of these intricate components by use of the water analogy would get us in deep water, where we don't want to go. Therefore, let's use a human brain to represent these detailed electrical components. Artist license is such a wonderful thing. Most turbine pumps need to be primed before they will start pumping water. In other words, they need to have a little water running through them before they can create enough suction to pump more water. Alternators operate in a similar manner. They need a little bit of electricity running through them before they'll start producing more electricity. This small amount of electrical prime is called the alternator field current. Take away this alternator field current at any time, and the alternator stops producing electricity. Water prime flows directly into the pump. Like alternators, our water pump needs to be continuously primed if it is to keep on pumping. The greater the prime, the greater the output of the pump. Alternators operate in a similar fashion. Varying the alternator field current varies the alternator's voltage output. When the engine is not running, prime for the pump comes from the battery. Water flows from the battery to the primary bus. It then goes to the alternator field circuit breaker, which is the left-hand side of a split rocker master switch. By turning on, pushing, the alternator side of the master switch, the left side, water flows into the voltage regulator, and a valve inside the voltage regulator. Prime, alternator field current, must pass through this valve to get to the pump for priming. The valve is controlled by the voltage regulator's brain. The brain then opens or closes the valve. This controls the amount of prime, alternator field current, reaching the pump. How does the brain know whether to open or close the valve? It senses the pump's output water pressure, or, in an alternator, its voltage. By comparing the pump's intake pressure with its output pressure, the regulator's brain can compute the precise amount of prime needed to produce the required water pressure. In electrical terms, these sense lines allow the voltage regulator to restrict an alternator's output to 14 or 28 volts of electrical pressure. When the master switch is turned on during engine start, the valve starts in the full open position, thus providing the initial prime. After engine start, the pump commences to produce water pressure or voltage, and the brain decides how much to close the valve to bring this output into regulation. It is in this initial startup period that the pump's output is momentarily unregulated, and you do not want your electrical equipment turned on. A sudden surge of pressure could damage this equipment, despite each piece of equipment having protective circuit breakers.
Now, folks, sometimes brains in a voltage regulator, just like in humans, behave errantly. Now, I recall a student pilot who was flying solo near the Southern California coast when he looked down and saw an aircraft carrier. A little devil on his left shoulder said, "Do it, do it." A little angel on his right shoulder said, "Yeah, do it." He did it. A carrier landing. Actually, more like a touch and go. The captain of the ship was not amused, neither was the FAA. It was a clear case of a brain gone astray. And it occasionally happens in voltage regulators as well.
When the brain in a voltage regulator goes south, it usually presents definite symptoms. You can expect either an over- or underproduction of voltage by the alternator. Problems with brains. Most aeroplanes have a warning light to alert pilots about alternator problems. The light is commonly known as either a high or low voltage warning light. When illuminated, it informs you that the alternator isn't supplying appropriate voltage to meet the system's electrical needs. If your aeroplane has a low voltage light, it can illuminate during low engine idle when there isn't enough RPM to develop even minimal voltage or pressure. Increasing the RPM raises the water pressure, voltage, and usually shuts off the light. A low-voltage light can also illuminate if the alternator has been taken offline because of excessive voltage production. This usually follows a popped alternator circuit breaker or alternator field circuit breaker. As far as the electrical system is concerned, no voltage is interpreted as low voltage. If your aeroplane has a high voltage warning light, it can activate when an overvoltage condition occurs. The alternator field current, the prime, is automatically removed, which takes the alternator offline. This keeps the circuits from being damaged by excessive system voltage. In either case, the activation of a high or low voltage warning light may follow a popped alternator or alternator field circuit breaker. When any circuit breaker pops, it is always worth paying attention. Personally, if I'm airborne and a circuit breaker pops, I don't reset it if the equipment it's protecting isn't essential. Resetting a circuit breaker is playing with fire, literally, and an in-flight fire is considerably less comforting than a campfire. If I need to use the equipment, I reset the circuit breaker once and only once, but only after letting it cool for several minutes. If it pops again, I leave it alone. In other words, it is not a good idea to reset a circuit breaker a second time. A popped alternator circuit breaker or alternator field circuit breaker takes the alternator offline. If you manually pop either of these, it produces the same result. Manually taking the alternator offline becomes an important consideration if an overvoltage condition occurs and the circuitry doesn't automatically isolate the alternator. Occasionally, a benign overvoltage condition exists, and the voltage regulator's brain automatically takes the alternator offline. This is sometimes called a nuisance trip-out.
Even human brains experience nuisance trip-outs. It happened to a student pilot in a Cessna 150. This fellow taxied out onto the runway and forgot his tail number, which is usually posted inside the airplane. Hoping to catch a glimpse of the number, he leaned out and slipped off his seat. He was hanging inverted, half outside, half inside the airplane, suspended by a loose shoulder harness. The funniest part was that he held on to the microphone and continued talking to the tower. I couldn't quite hear what he said, but I think it was, tower, I think I've fallen out and I can't get back in. I ran over and helped this guy back into his plane. I'm just glad he didn't forget his tail number while he was airborne.
Mental nuisance trip-outs are often amusing. In airplanes, they're simply annoying. The brain in the airplane's voltage regulator is subject to similar behavior. A nuisance trip-out may be indicated by a low-voltage light or an overvoltage warning light, depending on how the airplane's electrical system is wired. We can attempt to reactivate the voltage regulator by turning the avionics master switch to the off position to protect the avionics from a power surge, resetting the alternator or alternator field circuit breaker if popped, then turning both sides of the master switch off then on again. This signals the voltage regulator's brain to give the alternator another chance to produce normal voltage. Should the low voltage or high voltage light illuminate again, something is seriously wrong with the system. Conserve battery energy and land at the nearest airport. Making connections. Having gone downstream with our water analogy model thus far, you now understand several important things about the limitations of alternators. First, if the battery is dead, the alternator isn't going to work. You can still start the engine by hand propping, but as explained earlier, this is a risky maneuver which is not recommended for those who enjoy being bilaterally symmetrical. Since the magnetos are independent of the aeroplane's electrical system, they generate their own energy for ignition when spun. According to our water analogy, however, with a dead battery, no prime is available to coax the water pump into developing water pressure. The water pump will turn, but it will not pump. No priming, no pumping. It's as simple as that. In electrical terms, without enough battery energy for the alternator field current, the alternator spins, but it doesn't produce any voltage. You will not have any electricity, nor will the battery charge. Second, if the brain in the voltage regulator goes bad and the alternator produces too much voltage, you can take the alternator offline. Pull the main alternator circuit breaker, located schematically between the alternator and the primary bus. Of course, this assumes that it hasn't already popped out on its own. You can turn off the alternator half of the master switch, which will shut off the alternator field current flow, thus deactivating the alternator. Pulling the alternator field circuit breaker eliminates the alternator field current flow and shuts down the alternator. Third, if you want to use the aeroplane's electrical equipment on the ground without starting the engine, you should activate only the battery half of the master switch. Leave the alternator half in the off position. This prevents alternator field current from flowing to the alternator, wasting precious battery power. It makes no sense to waste battery energy to prime the alternator if it won't be in use. Airborne electrical emergencies caused by voltage regulator problems require conservation of battery energy. These situations should also be dealt with by turning the alternator half of the master switch to the off position. If faced with an errant voltage regulator in flight, Unload the system by turning off all non-essential equipment. This includes the waterbed heater and the disco strobe lights if they are installed on your Cessna 172. See if this returns the needle to a normal deflection. If not, then deactivate the alternator by turning the alternator half of the master switch to the off position. Let the battery provide the energy needs temporarily. This will allow an overheated voltage regulator to cool down, assuming that's the problem. After 5 to 10 minutes, reactivate the alternator by turning the alternator half of the master switch back on. See if the voltage regulator functions normally. If not, then deactivate the alternator by turning the alternator half of the master switch off and land as soon as practical. I've had great success with this cooling off period approach. Most voltage regulators have moving parts, relays, and contacts that can stick when subjected to high heat loads. Cooling lets the components contract and return to their normal position. If this doesn't work, then it's best to leave the alternator offline, conserve electricity, and head towards an airport for repairs. Drawing it all together. The first introduction to the electrical system in ground school is traumatic for most students. After the first view of a schematic, many students sit limp, eyes bugged as if they've been hit by a megawatt stun gun. I hope the water analogy makes consumption of this technical subject more palatable. Post-flight briefing number 4-1. Contact. How the battery contactor works. An aircraft battery, very much like a car's battery, stores a tremendous amount of electrical energy. Anyone who's ever banged cables together while jump-starting a car has seen the sparks fly. This is raw electrical energy on tap. Controlling this amount of current from the cockpit would require a rather large, well-insulated switch. In the cockpit, however, big switches mean increased weight, cramped space, and a greater chance of sparks flying during a malfunction. Aeroplane engineers prefer a more indirect means of battery control, the battery contactor. The battery contactor allows a small switch, the battery half of the master switch, to control a great deal of electrical energy. It gives an itty-bitty switch galactic power switching ability. Activating the battery half of the master switch closes a solenoid in the battery contactor, the big switch, allowing battery energy to flow directly onto the primary bus. Activating the battery half or the right side of a master switch allows water to flow from the positive terminal of the battery into the battery contactor. As current enters the contactor, a small amount splits off and flows to a small turbine/pulley arrangement. Water flows over the turbine, spinning it counterclockwise. Then it flows out towards the battery half of the master switch. From here, it flows to the ground. Remember, we learned to think of the electrical ground as a thin pool of water underlying our plumbing circuitry. This completes the flow of water through the master switch. An interesting plumbing reaction occurs when the turbine spins counterclockwise. A pulley is connected directly to the turbine and has a small rope wrapped around it that connects it to the on-off lever of a valve. When the pulley spins counterclockwise, it pulls the lever down and opens the valve. This lets the water from the battery flow through the valve, pressurizing the primary bus. In reality, a solenoid relay device in the battery contactor takes the place of a turbine and valve. Perhaps the most important item to be understood from this battery contactor model is that a small flow of water allows a larger flow of water. A small flow of electrical current, controlled from the cockpit via the master switch, allows the safe management of large amounts of battery energy. Remember, the water model is for electrical cause and effect understanding only. Don't take it literally. but do take the electrical results of our model's operation as fact. In the actual battery contactor, a solenoid opens the valve. Activating the battery half of the master switch sends a small amount of current flowing through a coil. This creates a magnetic field that pulls a heavy-duty relay down onto the two circuit points. Electricity now flows from the battery to the primary bus between these contact points. Turning the battery half of the master switch off prevents water from flowing over the turbine. This allows a spring to pull the valve's lever upward into the off position, which shuts off battery power to the primary bus. In a similar manner, placing the battery half of the master switch in the off position releases the pull on the solenoid. The relay pops up, preventing electricity from flowing to the primary bus. There is a one-wave flow valve connecting the contactor to the positive side of the battery. This is known as a clipping diode in electrical parlance. It's designed to avoid voltage spikes across the coil relay, caused by a collapsing magnetic field when turning off the master switch. What was that? A clipping what? Here's another way of looking at what a clipping diode does. Turning off the battery half of the master switch causes the turbine to momentarily spin in a clockwise direction. This occurs because the spring pulls the valve's lever shut and unwinds the pulley. Having taken a reasonable amount of artist's license with this model, let's look at what it helps us understand. Unless a slight amount of battery energy exists, the battery contactor isn't going to work. Remember, it takes a slight amount of water pressure from the battery to pull the valve's lever open. Only the battery can provide the initial energy to activate the battery contactor. If the battery contactor doesn't work, water will not flow from the primary bus to prime the water pump. In electrical terms, if the alternator field current isn't available, the alternator won't work. Inability to activate the battery contactor is another reason why an airplane with a dead battery or very low battery can't have its battery recharged by running the engine. After engine start, assuming enough battery energy, the water pump will immediately provide water pressure to the primary bus. From the primary bus, water flows through the charge-discharge ammeter, if your airplane has this type of ammeter, and down through the open valve and into the battery. It does so until the battery is charged. Remember, the battery may have lost a little of its charge by operating a current-hungry starter or by operating the radios prior to engine start. Because the pump is charging the battery, the ammeter has a deflection to the positive side. If your airplane has a load meter, it would indicate the water pump's output. If the battery's charge is low, expect an ammeter needle deflection to the positive side until the battery regains its 12 or 24-volt charge. Similarly, expect the load meter needle to indicate an alternator output slightly greater than required by all of the electrical equipment in use while the battery is being charged. When the battery is charged, water no longer flows from the primary bus to the battery. Nevertheless, a slight amount of water continues to flow through the valve over the turbine, thus keeping the valve open. This explains why the charge-discharge ammeter needle remains nearly centered in a healthy electrical system with a fully charged battery. Once the battery is charged, a load meter should show the approximate energy drained by the electrical equipment in operation. Readings higher than this should arouse a pilot's suspicion about the health of the electrical system. At this time, it is suggested that you review the illustrations and photographs in Chapter 4 of Rod Machado's Private Pilot Handbook. Chapter 5. Flight Instruments. Clocks, Tops, and Toys. Not everyone remembers their first date, but just about every pilot remembers his or her first look inside the trainer plane. Eyes riveted on the instrument panel, prospective pilots tend to respond with one- or two-word explicatives, followed by a swelling tide of self-doubt.
That was Rod's experience. Opening the door of an early model Cessna 150, he peeked inside the cozy two-place trainer and muttered the two-word initial response. His instructor, standing patiently nearby, was eager to offer encouragement and said, "Well, what do you think?" Rod said, "Man, you sure can tell what time it is with all these clocks in here." "Clocks? Those aren't clocks, those are flight instruments," the instructor barked, while rapidly recalculating the wisdom of trying to teach Rod to fly. Then he said, "In a very short time, they'll become your best friend." Rod thought to himself, those instruments and the IRS.
Well, it turned out to be true, at least about the instruments. If there is such a thing as pilot-instrument bonding, I experienced it. I learned to appreciate, respect, and enjoy all those dials on the panel, except for one, the Hobbs meter. The meter which keeps track of how long the engine is running, and from which your flight school calculates how much you owe. Flight instruments provide you with valuable, essential information. Extracting and interpreting that information through our 5 sensory organs is the challenge we're about to address. There are 6 basic flight instruments found on most airplane panels. These instruments are airspeed indicator, attitude indicator, altimeter, vertical speed indicator, heading indicator, and turn coordinator. Above the panel near the top of the windscreen, you'll also find the magnetic compass. Although orphaned from the panel, the magnetic compass is as important as any of the other 6 instruments. You're probably thinking, do you need all these instruments to pilot a plane safely? It's certainly possible for a more experienced pilot to fly visually and by feel while looking out the window. This, of course, is done in visual meteorological conditions, VMC, when weather permits visibility above certain minimums specified in the rules. These instruments, however, make it much easier for you to maneuver the aeroplane precisely. Where the flight instruments really earn their keep, though, is in instrument meteorological conditions, IMC, otherwise known as clouds. While you shouldn't be in the clouds without an instrument rating, an advanced license, these 6 instruments can help you save your bacon should you accidentally fly into a cloud. All student pilots learn how to extricate themselves from this situation during their private pilot flight training. All 6 instruments, each in its own way, provides you with information on 3 things: airspeed, height, and attitude. Airspeed is a measurement of the aeroplane's velocity through the air. The altimeter and vertical speed indicator provide information about your height above sea level, as well as how fast your height is changing. The heading indicator, turn coordinator, and attitude indicator provide information on the aeroplane's attitude. In other words, the degree of nose-up or nose-down pitch, as well as the amount the aeroplane is banked. Flight instruments will talk to you, if you let them. They speak a distinctive language, and the ability to hear and interpret it quickly and correctly is an important pilot skill. To fly without understanding your flight instruments is very uncomfortable and potentially dangerous. It's like the proverb that says, "One day the lion and the lamb shall lie down together." Maybe, but you can be sure the lamb won't get much sleep. It's time to learn to speak the language of the panel. Let's start our examination with the non-gyroscopic instruments. Non-gyro instruments. Airspeed indicator. The airspeed indicator is a wind indicator. It tells you the amount of wind blowing over the wings of your aeroplane as a result of your aeroplane's movement. Such information is useful for several reasons. First, with sufficient speed, the aeroplane will fly. The airspeed indicator then lets you know when it's safe to point the nose upward during the takeoff. Second, the airspeed indicator lets you know when you're above or below any of the aeroplane's critical speeds, in other words, the stall speed, maximum flap speed, maximum gear speed, never exceed speed, etc. Airspeed indicators work by sensing the impact pressure of air. Part of the airspeed indicator is connected to the pitot tube, which I pointed out as we circled the aeroplane in Chapter 1. High-velocity air rushes into the pitot tube and applies pressure within the metallic bellows located inside the body of the airspeed indicator. Expansion of the bellows is mechanically converted into movement of the airspeed needle via a gearing system. The container surrounding the bellows is connected to a static line, which connects to a static pressure source. A static source allows non-moving or static air to enter the airspeed container. This is simply the natural weight of the atmosphere, otherwise known as atmospheric pressure. A reading on the airspeed indicator is nothing more than the difference between impact air pressure entering through the pitot tube and static air pressure surrounding the metallic bellows. Let's take a closer look at air pressure and how it's measured. Static pressure. Imagine you are sandwiched between a bunch of leotard-covered professional wrestlers. You are halfway from the top. Your friend Bob is on the bottom. Who feels the greater weight or pressure? Why, of course, it's Bob. He has more people above him than you do. Therefore, he experiences greater pressure. Atmospheric pressure behaves in a similar fashion. Imagine air molecules piled up on top of one another like professional wrestlers. At sea level, there is a great deal of static air pressure or weight because there are more molecules at the top of the pile. As you ascend, there are fewer air molecules above you. Atmospheric pressure or weight decreases with a gain in altitude. Since static pressure is the weight of non-moving air, how does an airplane measure something non-moving while it's in flight? The static port is the perfect device for such a task. Being flush against the side of the fuselage, out of the way of air striking it, the static port lets the natural weight of the air, or atmospheric pressure, enter through its opening. Two additional instruments also require static air pressure to function: the vertical speed indicator and the altimeter. These instruments are also connected to the static port. We'll discuss these instruments later. Pitot tubes. Pitot tubes and static ports were discussed earlier. They can be found located in a variety of places on an aircraft. A common location for the static port is on the front left side of the fuselage. Pitot tubes are most often found under the left wing. Insects are a potential difficulty as they don't drain well. On several occasions, while giving flight instruction, I've had a small insect dive right into the pitot opening. Once, while approaching to land, a small bumblebee bumbled into the pitot tube opening. If the pitot opening is occluded by anything, animal, vegetable, or mineral, there is no impact air reading. This results, unfortunately, in an airspeed reading of 0. The student who was with me looked at the airspeed indicator and did what anyone would do to solve a similar problem. He hit it. In fact, he was reaching for his airspeed indicator repair kit, his shoe, when I calmly reminded him that he should be able to land the aeroplane without having to look at the airspeed indicator. He did a fine job. The airspeed indicator's face. Modern airspeed indicators are color-coded. This is not for your convenience in picking one that matches your airplane's carpet or curtains. Each of the colors is there to give you a piece of vital information about airspeed limitations. 4 colors are used on single-engine airplanes: white, green, yellow, and red. The white arc of the airspeed indicator, as we learned earlier, represents the aeroplane's flap operating range. The beginning or low-speed end of the white arc is the power-off stall speed in the landing configuration, in other words, with flaps fully extended and gear down. This is called VSO. An easy way to remember this is to think of the velocity, v, of stall, s, with everything out, o, or VSO. Of course, by out, I mean flaps fully extended and gear fully extended, assuming, of course, it's a retractable gear aeroplane. If the bottom of the white arc is at 53 knots, at VSO, the airplane needs a minimum of 53 knots of wind flowing over the wings to become or remain airborne. The assumption here is that the airplane is always at its maximum allowable landing weight, since the airplane is configured for landing, in other words, gear and flaps down. Lighter weights reduce the stall speed below the colored minimum. For your information, all color-coded stall speeds can also be the minimum steady speed at which the airplane is controllable. Either definition is correct. Following the white arc clockwise, we come to its high-speed end. This represents the maximum airspeed at which you may extend the flaps or fly with them extended. Called VFE, or velocity, V, of flaps, F, extended, E. Flaps may not be used above this speed for fear of structural damage, and the prime directive of any pilot is to avoid breaking the aeroplane. Most things green are good: money, guacamole, traffic lights. A green arc represents the normal operating range of the aeroplane. The beginning of the green arc represents the power-off stalling speed or minimum steady flight speed in a specified configuration. For the small airplanes we fly, this configuration occurs when the aeroplane is at its maximum takeoff weight and the flaps and gear, if retractable, are up. This is called VS1, or velocity, V, of stall, S, with everything inside, 1. Think of the 1 as the letter I, representing gear and flaps up or inside. The top end of the green arc is called VNO, or the maximum structural cruising speed. Since the green arc is the airplane's normal operating range, think of the top of the green arc as the velocity, V, of normal, N, operation, O. At and below VNO, airplanes have been certified to withstand substantial vertical gusts of air without experiencing structural damage. Vertical gusts of 30 to 50 feet per second, depending on the date of airplane certification. Operations above VNO, within the yellow arc, are allowed only in smooth air. Airplane wings are subject to a great deal of structural stress at higher airspeeds. Turbulence is a jolt of stress. If you add such a jolt to the stress of high speed, there are no promises about the wings remaining with you. Because the wings are very important, and because seeing them out there is such a comfort to most pilots, we'll talk more about handling turbulence in a bit. There is one speed you should never exceed. Coincidentally, this speed is called VNE, or velocity V, that you never, N, exceed E. This is the red line on the airspeed indicator. It's also the maximum speed at which the airplane can be operated in smooth air. Things are painted red, by us or Mother Nature, when they are of critical importance: blood, chili peppers, traffic lights. Above red line, all bets are off. I hope you're getting test pilot pay if you fly beyond this speed. Exceeding VNE can cause flutter, an uncontrollable and destructive vibration of certain airfoil surfaces, dynamic divergence, or aileron reversal. Take my word for it, these are bad things. On the other side of the red line lies territory no pilot should ever deliberately explore without packing a parachute. Consider this your Surgeon General's warning to avoid flying above the airspeed indicator's red line. V&E is 90% of the speed at which flutter occurs. Yes, there is a slight built-in safety factor, but don't ever count on built-in safety factors. Besides, you aren't being paid as a test pilot. If you want thrills, go bungee jumping, or bullfighting, or bungee bullfighting. That's where they dangle the bull from a crane, which suggests an entirely new line of Velvet Matador pictures. There are 3 other important speeds, and they're not shown on the airspeed indicator. The first one is called maneuvering speed, or VA, otherwise remembered as velocity, V, of acceleration, A. In turbulence, you should be at or below maneuvering speed. I said the yellow arc is for smooth air operations only. In strong turbulence, however, the only way to ensure that you won't exceed the aeroplane's structural limit is to fly at or below its maneuvering speed. Maneuvering speed is found well below VNO. Your pilot's operating handbook or posted placards provide you with the aeroplane's maneuvering speed. The last 2 speeds not shown on the airspeed indicator are VLO and VLE. These speeds refer to operation of the aeroplane's retractable landing gear, if equipped with retractable landing gear, of course. The velocity, V, of landing gear, L, operation, O, or VLO is the maximum speed at which the gear may be raised or lowered. The velocity V, with the landing gear L extended, E, is the maximum speed at which the aeroplane can be flown with the gear down. When the gear is in transition, it is often more vulnerable to the effects of speed. Once down and locked into position, the gear is able to resist a larger wind force. This is why VLO is often much less than VLE. These 2 speeds are found either in your pilot's operating handbook or on placards. Indicated airspeeds. You will soon find that many things in aviation come in several styles and flavors. Altitude is one of those, and so is speed. Unlike being on the ground, where speed is speed, though it can be expressed in different units such as miles per hour or kilometers per hour, there are a variety of aeroplane speeds, each with its own significance to you, the pilot. The number showing on the airspeed indicator is, sound of a drum roll, the indicated airspeed. If the airspeed needle pointed to 80 knots, then 80 knots is the indicated airspeed. It sounds too simple, doesn't it? It's somewhat like the question, what time does the 11 o'clock flight leave? When a controller asks for your current airspeed, he or she expects to get back the indicated airspeed. Controllers typically ask for this information by saying, Cessna 1234 Alpha, say airspeed. Those unable to resist the temptation to reply, and I quote, airspeed, unquote, can expect to find a strange and inexplicable increase in their arrival and departure delays. Calibrated airspeed. It's an imperfect world, and that's nowhere more evident than in aircraft instrumentation. The indicated airspeed is subject to, although slight, errors due to a variety of factors, including placement of the pitot and static sources, mechanical inaccuracies at various places in the range, etc. Like a trusty though cranky watch, if you know the amount of error, you can at any time correct the indicated time to get the actual time. The corrected, accurate reading is referred to as the calibrated airspeed, often written as CAS. Here's an official aviation secret. While very important on FAA knowledge exams and to flight instructors who enjoy dabbling in such things, The differences between indicated airspeed and calibrated airspeed are generally much smaller than the inaccuracies caused by the small size of the dials you're attempting to read and the differences in angle at which you read them. There are very few pilots who can discern the difference between 56 and 58 knots on a small instrument with a fat pointer which they're looking at from an angle that makes parallax a serious vocabulary word. Differences between indicated airspeed and calibrated airspeed are slightly larger at slower airspeeds and with flaps extended, as well as at higher cruise speeds. But overall, these differences aren't worth worrying about. Besides, the errors at slower speeds usually work in your favor, since your calibrated airspeed is usually higher than your indicated airspeed. In other words, you're going slightly faster than what you think you are. Don't worry, be happy. To facilitate this, we'll refer only to indicated airspeeds for the rest of this book. While indicated airspeed represents the amount of wind blowing on the aeroplane, it doesn't reflect the aeroplane's true speed through the air. Welcome to Aviation Paradox number 101. True airspeed. Indicated airspeed isn't the true airspeed, also written as TAS. While I promise to always tell you the truth, the airspeed indicator is incapable of such a promise. It's also incapable of such a performance through no fault of its own. It's the air's fault. Air at sea level is very dense. Drag is obviously quite high, since air molecules are packed closer together. As the aeroplane ascends, it experiences less dense air. This means less drag since fewer air molecules are around to resist the aeroplane's forward motion. Aeroplanes flying at higher altitudes actually move faster through the air for a given power setting because of the decrease in density. No problem, plane goes faster, airspeed indicator goes up. Yes, but it doesn't go up as fast as the real airspeed. While the airplane goes faster through the thinner air, there are fewer air molecules striking the pitot tube and expanding the bellows of the airspeed indicator. The result is that at higher altitudes you are moving faster than your airspeed indication shows. Space shuttle astronauts are cruising around at approximately 17,500 miles per hour while in low Earth orbit. They have a very high true airspeed. Would this true airspeed be shown on the shuttle airspeed indicator? We'll assume it has one. Hardly. There are too few air molecules to even flicker an airspeed needle at that altitude. If you ever achieved a low Earth orbit in your little Cessna 152, orbit-o-matic, you would also have a zero indicated airspeed, but you wouldn't notice since your blood would be boiling, and that always puts a damper on my flights. True airspeed is one of those concepts that seems to give you something for nothing. One time my dad came home and told me we were getting a new swimming pool. I was excited until he told me to go out to the car and bring it in. There's always a catch. Not so with true airspeed. You actually go faster and use less fuel up to a point as your altitude increases. Dense doings. You must be thinking, hey, if I go faster by flying higher, why not fly real high? Nice try, but it won't fly. This logic doesn't hold water or air due to the perversity of nature and aviation. A little while ago I said TAS, true airspeed, increases with altitude for a given power setting. Notice the for a given power setting part. It's the equivalent of the fine print in a contract from an aluminium siding sales representative. As you climb, the ability of the engine to produce power decreases due to the reduced air density. So the very thing which allows you to fly faster for a given amount of power, thinner air, limits the power you can produce. That's what I mean about the perversity of aviation. Turbocharging, as we discussed earlier, helps, but it too eventually runs out of steam. Your pilot's operating handbook identifies altitudes where you'll obtain the greatest gain in true airspeed for a given decrease in engine power. Two factors affect air density: pressure and temperature. Is there some way to precisely predict your true airspeed? Yes, and you don't have to be psychic to do so. The other day I called the psychic hotline, and they told me they saw a big phone bill in my future. Fortunately, true airspeed prediction is a little more precise. Some airspeed indicators have a movable ring on their outer scale to make determination of true airspeed easier. Just set the outside air temperature on the outer ring directly over the pressure altitude on the inner ring. The number to which your airspeed needle points on the outer ring is your true airspeed. Soon I'll show you how to use a flight computer to determine your true airspeed based on the altitude and temperature conditions. The altimeter. Welcome to the third dimension. One of the things making aviation unique is your ability to operate in 3D. No, you won't need any of those funny colored glasses, but you will need some assistance figuring out where you are in the third dimension. This is why I would now like to introduce you to your altimeter. Aeroplanes move left or right with great precision, flying specific headings and airways. This is two-dimensional navigation. Altimeters allow airplanes to fly at specific altitudes, a third dimension, with equal precision. There are lots of ways to get high in aviation, all perfectly legal and honest. Really. In the next few minutes, you will discover that there's altitude, and then there's altitude. Knowing one from the other is crucial to your success as a pilot, not to mention your longevity as a person. An altimeter provides you with your height above sea level, otherwise known as your true altitude. Sea level is a worldwide standard, therefore it's a consistent reference for altimeter measurement. Altimeters do not directly tell you your height above the ground. Why? The ground isn't a consistent reference. Ground height varies dramatically. If, however, you know how high you are above sea level, and you also know the ground's height above sea level, this is found on navigational charts, then finding your height above the ground is simply a takeaway math problem. Height above ground is technically known as your absolute altitude. An altimeter works by measuring the difference between sea level pressure and pressure at the aeroplane's present altitude. Inside the altimeter is a small, expandable capsule somewhat similar to a metal-skinned balloon. They're actually called aneroid wafers. The expansion or contraction of the capsule is mechanically converted into a movement of altimeter hands, resulting in an altitude readout. The altimeter's case is connected to the static port. This allows static air pressure to surround the capsule. Any change in static air pressure is then reflected by an expansion or contraction of the capsule, providing the altitude readout. To understand precisely how this process works, we need clearer understanding of how atmospheric pressure changes with height. Atmospheric pressure used to be measured by a mercury barometer. A tube of the heavy liquid metal mercury is filled and placed upside down in a vat of mercury. The weight of the mercury inside the inverted tube creates a small vacuum as the column attempts to sink out of the tube and into the vat. It's the vacuum that prevents the mercury from entirely sinking into the reservoir. The column finally stabilizes at a certain height. Let's say the height is 30 inches of mercury, sometimes abbreviated Hg, which is the chemist's symbol for the element mercury. Decreasing the atmosphere's pressure on the reservoir surrounding the tube allows the column to decrease in height. Increasing atmospheric pressure pushes on the reservoir, moving the column upward into the tube and increasing its height. The changing height of the mercury column represents atmospheric pressure in much the same way your tongue might represent the pressure of someone standing on your chest. A tongue, sticking way out of your mouth, would represent a lot of pressure on your chest. When the person stepped off your chest, your tongue would, we hope, recede into your mouth. One might be able to calculate the person's weight by measuring the exact amount of tongue protrusion. One might say that 200 pounds is worth 6 inches of tongue. Of course, I say this tongue-in-cheek, since it's not all that accurate. After all, it's only a rule of tongue, and calibration would always be a challenge. Even if we calculated tongue protrusion for a given amount of weight, this information is totally useless, but high in entertainment value nevertheless. There is, however, great value in calculating the height in inches that a column of mercury will change if it's moved vertically. Since the weight of the atmosphere changes with height, this pressure change would be reflected by a lengthening or shortening of the mercury column. Indeed, this is exactly what happens. For the purpose of altimeter calibration, a column of mercury will change approximately 1 inch in height for every 1,000 feet change in altitude. Let's say that at sea level, under typical pressure conditions, our mercury column stands 30 inches tall. We say the atmospheric pressure is 30 inches of mercury. At 1,000 feet above mean sea level, the pressure decreases and the mercury column falls approximately 1 inch. It now stands 29 inches tall. The atmospheric pressure at 1,000 feet MSL is properly stated as 29 inches of mercury. Altitude measurement is based on the consistency of this known pressure change. Aircraft altimeters don't use mercury barometers. If they did, there would be a big 3-foot-long tube protruding from the instrument panel. Not a pretty sight. Besides, it would keep poking you in the eye. Instead, the small expandable capsule's expansion or contraction is calibrated in inches of mercury. In other words, taken from sea level to 1,000 feet MSL, the capsule expands a small but predictable amount. Altimeter designers calibrate this change as equaling 1 inch on the mercury barometer. Now you are ready to understand how altimeters can determine your aeroplane's height above sea level. If an altimeter is resting at sea level, where the pressure is 30 inches of mercury, this is the pressure sensed through the aeroplane's static port. Therefore, the pressure surrounding the expandable capsule is also 30 inches of mercury. Let's say the pressure inside the capsule is also at 30 inches of mercury. What's going to happen to the capsule? Will it expand? No. The pressure inside the capsule is the same as the pressure outside the capsule. Without any pressure difference, the capsule doesn't expand, and the altimeter reads an altitude of 0 feet. Now let's take the altimeter to an altitude of 3,000 feet MSL. The static pressure at 3,000 feet is 27 inches of mercury. If the pressure inside the capsule is still 30 inches of mercury, what will the capsule do? Yes, it will expand an amount equal to this difference in pressure. It will expand by an amount of pressure equal to 3 inches of mercury. This expansion equates to a 3,000-foot reading on the altimeter's face. Remember, the capsule expands because its internal pressure is greater than the outside static pressure. Pressure variations and the altimeter. If the pressure at sea level always stayed at 30 inches of mercury, this would be the end of our altimeter story. Unfortunately, the pressure at sea level varies daily, hourly, and sometimes even minute by minute. The atmosphere actually changes weight slightly. causing air to push down harder on some parts of the Earth than others. In the weather section, you'll have a chance to study these pressure differences more thoroughly. For now, let's agree that the pressure at sea level changes often. The altimeter's job is to measure the difference between sea level pressure and the outside static pressure of the altitude at which you are flying. As we've already learned, the difference between these two pressures allows the altimeter to calculate your height above sea level. Since we've already agreed that sea level pressure changes at a fixed location, think about how quickly it can change when moving across the country in your aeroplane. You obviously need some way to keep your altimeter informed about the changing pressure at sea level. A small knob at the front of the altimeter allows you to do just that. Twisting this knob rotates the little numbers in the Colesman window on the face of the altimeter. It also rotates the hands which indicate altitude. This is the pilot's way of telling the altimeter what the pressure is at sea level. Changing the numbers in the Colesman window recalibrates the pressure inside the altimeter's expandable capsule. This is done mechanically by repositioning an internal linkage which gives the capsule a new starting point from which to begin measuring. Whatever pressure you set in the Colesman window, the altimeter assumes this is the new sea level pressure. Now the altimeter measures the difference between the pressure value set in the Colesman window and the outside static pressure to obtain your height above sea level. For instance, when 30.10 inches of mercury is set in the Colesman window, the pressure inside the expandable capsule is recalibrated to 30.10 inches of mercury. Now the altimeter thinks the sea level pressure is at 30.10 inches of mercury. Setting to 9.95 inches in the Colesman window tells the altimeter the pressure at sea level is 29.95. If an airplane is over San Francisco, where the sea level pressure is 30.25 inches of mercury, this value is set in the Colesman window. The difference between 30.25 and 27.25 is 3 inches of pressure, or 3,000 feet. The altimeter reads 3,000 feet, the aeroplane's true altitude. Here's a note. As you'll soon see, to obtain true altitude, you also need to correct the altimeter for non-standard temperature variations. For now, we'll just assume that the true altitude is obtained by correcting the altimeter for pressure changes. If a second aeroplane is over Santa Barbara, where the sea level pressure has lowered to 29.25 inches of mercury, the static pressure at that aeroplane's altitude of 3,000 feet is 26.25 inches of mercury. The difference between these two is 3 inches. Therefore, the altimeter reads 3,000 feet. The point is that we should always set the sea level pressure in the Colesman window so our altimeter can read true altitude. Okay, you wonder, how do we get the sea level pressure to set in the Colesman window in the first place? The sea level pressure is called the altimeter setting. It's easily obtained from several sources including air traffic control towers, flight service stations, and automatic weather observation stations. A bit later in this chapter, I'll tell you about one more way you can get the right altimeter setting, even when nobody's home at the tower. What happens if you don't continue to update the altimeter setting during every 100 miles or so of flight? There's a good chance your altimeter will not be providing the correct information. You're not going to be at the altitude you think. This can be a problem. Think of the problem as being similar to driving across the country while listening to your car radio. If you're listening to a lecture about yin and yang on that philosophical radio station KYMI, after a short distance you'll need to retune to another station carrying the same program. You'll be out of range of the first station. If you fly more than 100 miles from the source of your last altimeter setting, you're technically out of range from this source. For example, let's assume the altimeter setting at San Francisco is 30.25, and at Santa Barbara the altimeter setting is 29.25. At 1,000 feet MSL above San Francisco, the pressure is 29.25. This is the same as the sea level pressure at Santa Barbara. Do you see how the 29.25 pressure level gradually sloped from 1,000 feet MSL over San Francisco down to sea level at Santa Barbara? It can be said that pressure levels drop when flying towards an area of lower pressure. At 3,000 feet above San Francisco, the static pressure is 27.25, with the altimeter setting at 30.25. Approaching Santa Barbara, the 27.25 pressure level slopes downward to 2,000 feet above the surface. With the San Francisco sea level pressure of 30.25 set in the Colesman window, the altimeter indicates 3,000 feet as long as you stay at the level where the outside pressure is 27.25. Can you see what's happening? The level where the pressure is 27.25 inches of mercury actually slopes downward closer to the surface, yet the altimeter is still reading 3,000 feet. If we don't continue to update the altimeter setting, the indicated altitude, what's shown on the altimeter's face, becomes different from our true altitude, our actual height above sea level. Over Santa Barbara, our indicated altitude is 3,000 feet, but our true altitude is only 2,000 feet above sea level. Is this a problem? Yes. What happens if there is a mountain at 2,500 feet along your path? Looking at the face of the altimeter, it appears you'll clear the mountain by 500 feet. In reality, you're 500 feet below the top of the mountain. Under these conditions, there's a good chance that your aeroplane's landing gear might conk the head of some camper sitting around a campfire on top of that hill. What a shock it would be if it were nighttime and you thought you would clear that 2,500-foot mountain by 500 feet. You might end up with a Coleman stove, camping gear, and raccoons stuck to your aeroplane. Suppose you're over Santa Barbara, and suddenly you realize your mistake of not updating the altimeter setting. You call the Santa Barbara Tower, and the controller tells you the altimeter setting is 29.25. He or she will actually say, altimeter setting is 29.25. The inches of mercury part is understood and never spoken. You set this in the Colesman window. For the remainder of this chapter, that is how we will quote altimeter settings. When the controller has given you the current Santa Barbara altimeter setting as 29.25, what will your altimeter read? The difference between the recalibrated pressure in the expandable capsule and static pressure is now 2 inches. Therefore, the altimeter reads a true altitude of 2,000 feet, at which point you immediately begin climbing back to your previously selected altitude of 3,000 feet. By updating the altimeter setting, the indicated altitude is now the same as the true altitude. Indicated altitude is what the altimeter shows. True altitude is your height above sea level. Good pilots make it a point to update their altimeter setting at least every 100 miles, if not more often. Did you notice that twisting the knob and moving the numbers down from 3025 to 2925 caused the hands to unwind 1,000 feet? From a strictly mechanical point of view, whenever the numbers in the Colesman window move downward, the hands also move downward. Changing the numbers 1 inch in the Colesman window is worth 1,000 foot altitude change on the altimeter's face. There's a very important point to be made here. When the altimeter is set too high, it reads too high in terms of altitude, and you will be lower than you think. Let me rewind the tape for you so you can hear that again. There's a very important point to be made here. When the altimeter is set too high, it reads too high in terms of altitude, and you will be lower than you think you are. If the altimeter is set too low, it reads too low. Flying from San Francisco to Santa Barbara toward an area of lower sea level pressure and not updating the altimeter setting means the barometric pressure setting in the Colesman window is too high. Therefore, the altimeter reads too high. In other words, the indicated altitude of 3,000 feet is higher than our true altitude of 2,000 feet. Now we'll consider an airplane flying from a low-pressure area toward a high-pressure area, in the opposite direction of our flight from San Francisco to Santa Barbara. If the airplane maintains a constant indicated altitude of 3,000 feet without updating its altimeter setting, the altimeter follows the 2625 pressure level, which slopes upward as the high-pressure area over San Francisco is approached. With the altimeter set too low, it will read too low, and you will be higher than you intend to be. The indicated altitude will be 3,000 feet, but you will actually be 4,000 feet above sea level when over San Francisco. If you had to pick the most dangerous flight scenario, it would probably be flying from high pressure to low instead of low to high. And this is generally the example which shows up on FAA tests and instructor interrogations. The point of all this is that you must keep the altimeter informed about the current altimeter setting. Regulations require you to adjust the altimeter to the current reported altimeter setting of a station along the route and within 100 nautical miles of your aeroplane. Keeping altimeters informed is similar to keeping your spouse informed. It produces a happy relationship. Temperature variations and the altimeter. Just when you think you've got all the exceptions down pat, another gem in need of consideration pops up. You just can't seem to win. It's like going to the 1-hour photo shop only to find out they have 30-minute parking. Don't fret. The altimeter's temperature errors are easy to understand. Normal changes in temperature produce relatively small and negligible errors in altimeter settings. If, however, you're taking the family's Boeing 747 out for a little cross-country flight, you could travel to exotic places having extreme temperatures, in particular extreme cold. Under these conditions, it's possible to have altimeter errors of 500 feet or more. Practically speaking, most pilots never correct their altimeters for temperature variations. Nevertheless, it's important to know when these errors can affect you and how to correct for them. Most of the time, pilots fly with plenty of terrain clearance and are not affected by small temperature-induced altimeter errors. On the other hand, if you're planning a night flight over mountains and don't plan on crossing them by at least 2,000 feet or more, you should check and see if temperature errors will significantly affect your altimeter's reading. You should also have a CAT scan to check for reduced blood flow to the judgment section of your cortex if you're crossing mountains at less than 2,000 feet above ground level at night. When air is at standard or normal temperature, remember that is 59 degrees Fahrenheit or 15 degrees Celsius at sea level, the altimeter experiences no temperature error. An airplane sitting on top of a column of normal temperature air has an indicated altitude of 4,000 feet, which is equal to its true altitude of 4,000 feet. When temperatures are warmer, however, air expands. If our aeroplane rests atop an expanded layer of air at 100 degrees Fahrenheit, the air beneath weighs the same as the air beneath an airplane on top of standard air. The difference is that the warmer, expanded column of air is taller. This is similar to two guys both weighing 370 pounds, with one standing 6 feet tall and the other standing 4 feet tall. They both produce the same indication on a scale, but their weight is distributed differently in the vertical direction. In a similar manner, a mass of air having temperatures that are different from standard distributed its weight differently in the vertical direction. Because the pressure levels are taller or expanded in warmer air, our aeroplane indicated altitude is 4,000 feet, and its true altitude is 4,250 feet. Colder air produces shorter or more closely spaced pressure levels. If the outside air temperature is 32 degrees Fahrenheit, our aeroplane's indicated altitude is 4,000 feet, and its true altitude is 3,750 feet. Think about it the following way. Without correcting the altimeter for temperature variations, if the temperature is going down, then the aeroplane is going down. If the temperature is going up, then the aeroplane is going up. On a flight from a warmer area to a colder area, without correcting for temperature, the indicated altitude is greater than the true altitude. In other words, the altimeter will indicate 4,000 feet, but the true altitude will be 3,750 feet. The temperature went down, so the aeroplane went down. It went down 250 feet, and you still think you're at 4,000 feet above sea level. On a flight from a colder area to a warmer area, without correcting for temperature, the indicated altitude is lower than the true altitude. By reversing our previous example, in the warmer area, the indicated altitude is 4,000 feet, but the true altitude is 4,250 feet. Therefore, if the temperature is going up, the aeroplane is going up. It went up 250 feet, and you still think you're at 4,000 feet above sea level. There's another excellent memory aid to help you keep these altimeter errors straight. When flying from high to low, look out below. This rule assumes that you forgot to set in the nearest altimeter setting or correct your altimeter for temperature extremes. You must look out below because you are not as high as you think you are. The statement, "look out below," should be an immediate cue of danger. Danger means that you are closer to sea level than your altimeter says you are. Suppose you're arriving or departing an airport under extremely cold temperatures. You should think, if the temperature is cold, then the thermometer has gone down. Therefore, the airplane is going down. In other words, your airplane's true altitude is lower than the indicated altitude. You already know how to correct for pressure variations during flight. You simply adjust the altimeter setting to the nearest station within 100 nautical miles of the aeroplane. But how do you make correction for variations in temperature? You can use your flight computer, mechanical or electronic, for these computations. Once again, we don't normally correct the altimeter for temperature variations unless the temperatures are extreme and we plan on crossing terrain at low altitudes. Sensitive altimeters. We call modern altimeters sensitive altimeters. This is not because they cry at movies. Sensitive altimeters actually have 2 or even 3 expandable capsules instead of 1. This allows them greater precision or sensitivity in altitude measurement. It's possible to hold a sensitive altimeter in your hand, move it from the floor to the ceiling, and record an altitude change. And poke a hole in your roof. Now that's sensitive. Suppose you're departing an airport early in the morning before the tower opens and no altimeter setting is available. Remember a couple of sections back, I promised you one more way to get a stealth altimeter setting. It's remarkably easy. Simply rotate the altimeter knob until the hands point to the field elevation. Field elevation is a number that's listed on almost all aviation charts and in many other published sources. This is what the hands would read if you had the current altimeter setting, isn't it? Now, in a backward sort of way, the numbers in the Colesman window give you an approximate altimeter setting for that area. At least this allows you to start your flight with a correct reading on the altimeter. However, as you progress along your route, keep updating the altimeter setting at least every 100 nautical miles. Remember, pressure at sea level can change quickly. The altimeter must be kept informed so it will provide accurate altitude information. Cross-checking the altimeter setting with the field elevation is always a good idea. You can sometimes catch a mistake in the altimeter setting you've heard or thought you heard by noticing that the resulting altitude is way off from what it should be for the airport. Do you remember our discussion on how ATC personnel determine the altimeter setting? I said you wouldn't believe it when I told you how they did it. Well, many of them do it with a small altimeter of their very own. They simply turn the knob until the altimeter reads the field elevation or elevation of the tower cab. Then they look at the numbers in the Colesman window. That's the altimeter setting they issue, and you thought it was done with smoke, mirrors, and controlled substances. Pressure altitude.
Every family has an Uncle Ed. He's the typical uncle who's just one taco short of a combo plate. Rod's Uncle Ed would always say he lived in a gated community, which Rod interpreted this to be prison. Uncle Ed would tell the type of jokes no one laughed at. He would always say, "Well, you had to be there." Rod contemplated that if he had been there, he would understand Uncle Ed's humor. The problem is, how does one get back there to understand?
A similar problem exists where airplane performance charts are concerned. When engineers create performance charts, they make them under specific altitude, temperature, and pressure conditions. To use these charts, you must go back to the conditions the engineers used when the performance computations were made. We call the day on which these specific altitude, temperature, and pressure conditions existed a standard day. For an engineer, a standard day occurs when the temperature and pressure at sea level is 59 degrees Fahrenheit or 15 degrees Celsius and 29902, respectively. Most of the airplane's performance charts are based on these conditions. Here's the problem. What if the temperature and pressure at sea level isn't a standard 15 degrees C or 29902? And it rarely is. Will these performance charts still provide you with reliable information? They will if you go back to standard day conditions. Let me show you how to do this with a performance chart. A climb performance chart requires two variables, pressure altitude and temperature, to determine climb rate. This thing called pressure altitude is the pressure condition the engineers experienced when they determined the aeroplane's performance. Since the pressure at sea level was 29902 when they tested the aeroplane, all you need to do in determining pressure altitude is set the altimeter's Colesman window to 29902 and read the indicated altitude. This reading is your pressure altitude. Using pressure altitude and the outside air temperature, we can determine our airplane's performance on the rate of climb chart provided in the pilot's operating handbook. Of course, once you've determined your pressure altitude, you should immediately reset the altimeter back to the altimeter setting provided by air traffic control. This keeps the altimeter reading the correct height above sea level, in other words, your true altitude. Remember, pressure altitude is used for performance computations. It's the height above a standard datum plane, which is nothing more than a fancy phrase for an imaginary reference point. This reference point is what the engineer's altimeter would have read if temperature and pressure at sea level was 59 degrees Fahrenheit and 29902. Reading the altimeter. Reading the altimeter is very similar to reading a watch. I say this with caution, knowing that some readers have been raised on digital watches and no longer know what it means when Mickey's little hand is on the 3 and his big hand is on the 12. Some may not even know which way Mickey's hands turn. I know this is a problem because the tower pointed out traffic for one of my students by saying, 32 Bravo, you have traffic at 2 o'clock. My student replied, well, it's only 1:30 and we've got half an hour before it gets here. A typical altimeter has 3 hands, which is how many you wish you had sometimes when things get busy in the cockpit. The shortest hand points to numbers representing the airplane's height in tens of thousands of feet. The medium, thicker hand represents altitude in thousands of feet, and the long, thin hand represents the airplane's altitude in hundreds of feet. On some altimeters, a very long, thin hand with a triangle on the end is substituted for the 10,000-foot indicator. The easiest way to read an altimeter is to read it just like you would read a clock. For instance, if the middle, thicker hand is pointing to the 3, and the long hand is pointing to the 0 at the top of the dial, it would read 3 o'clock. Since an altimeter isn't a clock, it shows an altitude of 3,000 feet. The long hundreds hand points to the 0, 100 feet, and the medium thousands hand points to 3,000 feet. Therefore, the altitude is 3,000 feet. If the altimeter were a clock, and the medium larger hand is between the 3 and the 4, and the long hand is at the bottom of the dial at 5, it would read as though it is 3:30, or half past 3 o'clock. As an altimeter, it reads half past 3,000, or 3,500 feet. The long hundreds hand points to 500 feet, and the medium thousands hand points between 3,000 and 4,000 feet. The altitude is 500 feet past 3,000 feet, or 3,500 feet. What time would it be if our altimeter's hands were in the following position? The long hand on the 8, and the middle thicker hand approaching the 7. It would seem to be indicating around 6:45. More precisely, the long hundreds hand shows 800 feet, and the medium thousands hand points a little shy of 7,000 feet. Therefore, the altimeter reads 800 feet past 6,000 feet, or 6,800 feet. Not too tough, is it? One final example. If the shortest hand of the altimeter is between the 1 and the 2, the medium hand is on the 3, and the long hand is on the 0, what time would it be? It would seem to appear as though it's 3 o'clock. But remember the smallest hand. This little hand points to a little past a value of 1, meaning you need to add 10,000 feet onto the value shown by the altimeter's medium and long hand. This altimeter indicates an altitude of 13,000 feet. Keep an eye on the 10,000-foot hand, especially on FAA tests. It can be tricky if you aren't watching for it. A good general rule of aviation is to always check everything. You're going to discover that the altimeter is a very handy little device. No pun intended. Not only is it useful for the obvious reason of maintaining a certain height above sea level, but it's also useful as a pitch instrument. Your first introduction to the altimeter will be during straight and level flight. I might warn you, this isn't two separate maneuvers, it's one. When my instructor first asked me for straight and level flight, I asked him, "Which one of these do you want me to do first, straight or level? I can't do them both at the same time." The altimeter is relatively sensitive to pitch changes. Any deviation from level flight should be noticed as a slight movement in the altimeter's 100-foot hand. You simply monitor the visual horizon to maintain a straight and level pitch, while occasionally checking the altimeter for needle movement. When haze or other forms of obscuration make the horizon difficult to identify, the altimeter can be critical in confirming you're in a level pitch attitude. Referencing the altimeter also provides you with pitch attitude feedback during steep turns. Since the horizon line changes quickly, glancing at the altimeter's 100-foot hand is a good indication of any deviation from the desired altitude. Sharp pilots make it a point to constantly reference the altimeter during any maneuver requiring a constant altitude.
Learning to use your altimeter and the other flight instruments properly should prevent the frustration Rod experienced as a student pilot many years ago. He was in the practice area with his flight instructor doing steep turns and having trouble maintaining altitude. During one turn, his altitude dropped from 3,500 feet to 3,000 feet. In a humorous attempt to deal with the problem, he reached up, grabbed the altimeter knob, and rotated it until the hands went back up to 3,500 feet. He looked over at his instructor and said, "Ah, the altimeter setting has just changed." His instructor looked back and smiled and said,
"So has the date you're going to solo." The vertical speed indicator, VSI. Also known as the vertical velocity indicator, or VVI, the vertical speed indicator is located in the bottom right hand of the instrument panel's six-pack of instruments. Calibrated to read in feet per minute, the needle swings upward or downward, reflecting the aeroplane's rate of climb or descent. The VSI case is vented to static pressure through an amazingly small opening called a capillary tube. It's also called an airflow restrictor. The expandable capsule connects to the static source via a normal-sized tube. At a constant altitude, the pressure in the case and the capsule are equal, and no climb or descent is shown. During a climb, air pressure in the capsule decreases, but air pressure in the case can't decrease as quickly because of the airflow restrictor. Therefore, pressure in the capsule is less than in the case, resulting in the capsule's compression, which is mechanically converted into a rate of climb indication. Precisely the opposite happens during a descent, when the capsule is at a greater pressure than the case, resulting in the capsule's expansion, which is mechanically converted into a rate of descent indication. You'll find the vertical speed indicator very useful in helping you plan climbs and descents. Suppose you're 10 nautical miles from an airport and traveling at 2 nautical miles per minute. In other words, a 120 knot ground speed. It takes 5 minutes to cover those 10 miles. If the aeroplane's altitude is 3,000 feet above the airport elevation, a descent rate of 600 feet per minute is required to reach the airport. While this is only a rough estimate, it does aid you in planning your descents. The VSI is also a useful instrument for detecting trends away from an established pitch attitude. We learned that the altimeter is very useful as a pitch instrument during straight and level flight, turns and steep turns. Frankly, I use the VSI more than I do the altimeter for determining changes in aeroplane pitch. During a steep turn, I'll scan the VSI and watch for needle movement. Any deviation from a zero reading is quickly corrected by a change in elevator pressure. While the instrument does have a slight lag, it is hardly noticeable when small, non-abrupt pitch changes are made. Alternate static source. A pilot reported downwind at one of our local airports on a quiet, calm morning. ATC said, 2132 Bravo, which runway would you like to land on this morning? The pilot replied, that one. To which the controller responded, could you point a little louder? Sometimes a pilot's brain is like an aeroplane's static source. It becomes clogged. Fortunately, for aeroplanes there's often an alternate source of static pressure in the event the primary source becomes plugged. Since the airspeed indicator, altimeter, and vertical speed indicator all rely on static pressure, any clogging of the static source will affect these instruments. In fact, a plugged static port will prevent any static air pressure change, causing the altimeter to freeze at its last indication and the VSI to read 0, regardless of altitude change. It will also cause the airspeed to be in error if a climb or descent is made. Fortunately, some airplanes have alternate static sources that tap into another source of static air pressure. If the primary static source becomes plugged, a little valve, normally located under the instrument panel above the pilot's knee, can be opened. Cabin static air pressure now becomes the pressure source for the airspeed indicator, altimeter, and VSI. Cabin static air pressure is slightly less than outside pressure, so selecting it will cause a slight, temporary jump in the VSI's indication and a small gain in altitude, usually less than 50 feet. This will generally be the least of your problems.